Thanks for introduction and thanks for hosting me. I chose to talk about something different today. So I think, in particular in front of Georg, I was talking too often about what I call the Bayesian machines. So basically machine learning and reasoning under uncertainty and how to accelerate this task and all this connection to analog and photonic computing. So basically today is something really different. It's about energy consumption, in particular for large-scale machine learning workloads. And basically the overarching story is that energy consumption is something I'm concerned with since about 10 years plus. But no one listens to me, and I'm not giving up, so I keep talking about it. And I think this time I actually have a little bit more involved story than usual. So basically from the overall kind of storyline, I will start with some fundamentals regarding my own mindset in this context, which is definitely my mindset, but I'm happy to share that one. And I'm also happy to hear comments on that one. And then I basically have one very concrete use case. Can we basically use this to reduce the energy consumption of LLM workloads, basically simply by something as simple as frequency tuning of the underlying GPUs. And then a little bit of other work, which is a little bit work in progress. So I wish I would be talking about more concrete results. But basically, the main part of the last, or maybe the last part is how can we connect our small research as a university research group to large-scale LLM training? And no, we don't have these 4,000 GPUs. And if we had them, we would be doing other things than that one, I guess. But it's like the overall storyline for today. And from that point of view, I'm trying to connect in an abstract manner these picojoules to the mentioned gigawatt hours. For my own personal background, actually having a quite bumpy overall career. So I started as a database engineer at some point in time in my life. In my PhD time, I was most of the time designing some hardware components. So either the package or even chips like this one over here, 180 nanometers, ridiculously large, but a big adventure back in the day. Over the years, I moved away from hardware simply because the time per paper was not sustainable. Too much work going on. So I basically switched first to FPGAs as an intermediate solution. Then also FPGAs were not sustainable, so I moved to the GPUs. And it was nice because focusing on these multi-GPU systems raised the attention of NVIDIA at some point in time. So I was actually working for NVIDIA, learned many lessons over there. And after NVIDIA, when I came back to Heidelberg, actually we got a nice research project granted, which was called Deep Chip. And this is basically the point in time in 2017 when in our group, deep neural networks took over. And basically everything we did before, high performance computing, databases, large scale graph databases whatsoever. No, today it's machine learning. And that's also the reason for this nice group name now, which is basically hardware and artificial intelligence as a combination. So basically we are trying to bridge these two fields. We're no longer designing our own hardware. So we're simply customers of other people, other smart people producing hardware, but we're trying to find a batch match in between this plethora of different hardware options. Could be standard like Raspberry Pi, could be standard like GPUs, could be exotic like analog and photonic processors, and try to connect them to the machine learning workloads, which in usual form are some variants of deep neural networks. And in this particular field, we feel very happy. So the group has a very, very interesting size nowadays. Basically, currently 2 postdocs, he just graduated, and a bunch of PhD students, not too many. But there's like a fleet of master students in the background, which are basically doing most of the work. And somehow I think they all come because of this combination of hardware and machine learning, which is not something one finds very often today. So as I see out there, the experts in machine learning, which have no clue about hardware, very often hardware people which have some knowledge about machine learning, but not in detail. And we're kind of trying to fill the gap in between. Good question regarding hardware and machine learning, where we are today and what is going to happen next. So on this slide over here, I was a little bit summarizing my own view on the hardware. So in general, the best thing you can buy for machine learning are GPUs. And it will be quite difficult to find spots where GPUs will not do the job. I strongly recommend reading this paper over there, the hardware lottery, as a nice message, which is basically GPUs as we know them today exist because deep neural networks exist. And deep neural networks as we know them today exist because, well, GPUs exist. And I can't deny that one. The main question I'm always having in mind is what would happen if you add another processor which would be as good as a GPU or a different form of neural network. This would be another point in time I would deviate to my Bayesian machines and tell everything about Bayesian neural networks and uncertainty and yada yada, but I'm not going to do this today. Today, the main message is that for LLM workloads, large language models, GPUs are a very, very nice, by accident, co-designed processor. The main worry I'm having in this context is, as you can see on the right side over here, this was a nice study by some HBM people, is the future scaling of GPUs. So as you can see over there, today we are at Blackwell, almost Rubin. For Rubin, the power consumption will double to more than 2 kilowatts. If we keep going afterwards, already announced is Feynman, then there will be something like post-Feynman and some next gen, and next gen is something like 10 or 9 years in the future. But basically the main message is you have to afford that power bill. And it will be 15 kilowatts in 9 or 10 years for one GPU. We have a quite nice building at Heidelberg University. I was in charge for organizing the computing rooms, and I basically negotiated for 60 kilowatts, which I'm very proud about, because before it was like 10 kilowatts, now we have 6 kilowatts. I know you're laughing about this one because it's a different scale over here, but this is like a not computing center building. We could afford 4 GPUs in that building, which is absolutely ridiculous. I'm not saying that you will not get any performance scaling anymore. So of course you will also get some performance scaling. Actually also the energy per operation will continue to scale down. But basically the main worry is that we are now at a point in time where Moore's law, better said, standard scaling really bites us, and basically affording this energy is at some point in time no longer sustainable. And this is basically the main motivation to talk about GPUs today. So if we assume that we have to keep relying on GPUs, which I assume for LLMs would be kind of a sweet spot for a foreseeable time, then we have to do something about it, which very often makes me, in my own mindset, remind me of what actually the fundamentals are. So on one hand, processors have a certain performance. So there's a certain instruction per cycle metric times the frequency, which translates into performance, whatever operations you're doing, how many can you sustain per time unit. But in reality today, everything is power limited. So I usually like to rephrase this equation in the following sense, that your ultimate performance you can sustain is rather limited by the power consumption in watts, which is then multiplied by the operational efficiency in operations per joule. So basically, assuming that the first part, the power, is a constraint, the only thing you can play with is the energy efficiency of an operation. This basically is my best connection from performance to energy efficiency. If you want more performance, you have to optimize your energy efficiency. If we break down the energy efficiency at over here into something more fundamental, then I still assume that energy is always additive, not like time. Time is not additive, but energy is additive. So basically, we can simply break it down into the sum of the energy spent for operation and the energy spent for the corresponding data movements. Anytime you do something, 2 operands go in, 1 go out. This will be some data movement. This will cost some energy. And for quite some time, I was reasoning about, okay, what is more important? But in a nutshell, I would argue that the energy for operation is basically highly dependent on the processor you have in front of you. So CPUs are doing a rather bad job for certain reasons, but GPU is definitely exhibiting much better energy per operation numbers than the CPUs. And FPGAs definitely also have their sweet spot in the setting over here. And for the memory part, basically, we can start reasoning, okay, where's our data coming from? So basically, the energy per data movement is a function of which memory are you talking to, possibly the cache hierarchy level, possibly also the physical distance, something like in units of millimeters. So the longer you move, the more often you have to amplify and reinforce the signals and all these things. And in a sense, it's basically super nice over here with the main caveat that in this world over here, something like latency tolerance doesn't exist. And if in this world latency tolerance doesn't exist anymore, then my main question would be that our main toolbox is also vanishing. I don't have a good answer for that one. I would rather go in a different direction and mainly ask the question, what is actually the importance of these two different components over here? So what does that hurt more in practice? And what can we expect in terms of technology scaling? And luckily, there were some nice numbers published. So this is basically here some tables summarizing different energy consumptions for operations like integer operations, multiply, add, floating point, and corresponding data movements. And basically all the data I found, and it was quite some effort to find this data, come from 2 papers. One is rather old, from 2014, from Horowitz, from Stanford, making experiments with a 45 nanometer technology. And the more recent one I learned about, I think it was second last year when I met a guy called Dave Patterson at a Darkstool workshop. And I asked him about recent energy numbers, and he was like, why don't you read my papers? And I was like, I should read your papers. And he said, yes, he was co-author of a TPU paper. It was the V4 one. And they published some numbers when producing that chip, and this basically was relying on 7 nanometers. In a nutshell, what we can see over here is a nice motivation for many games to play in optimizing deep neural networks. So instead of doing floating point operations, which are quite costly in terms of energy, a couple of picojoules, Another want to do integer operations. In machine learning language, you want to quantize your deep neural network. Quite similarly, energy for memory is way more expensive than for calculations. So you don't want to talk to memory, so you introduce sparsity, which the machine learning people call pruning. So basically, this also serves as my main motivational slide when I start talking about all the things we are doing in terms of compressing deep neural networks by quantization and pruning. And some side effects. So additions are way more expensive than multiplications and similar things. So if you find fancy algorithms which avoid multiplications at the cost of my additions, this is definitely something which is a reasonable game to play in this setting over here. As mentioned before, energy is way more expensive. Sorry, data movements are way more expensive than data movements. And we can also see that the energy for data movements is not scaling as nicely as the energy for calculations. This is something was predicted by the device community, which are producing these transistors. And the main footnote is that we saw some nice improvement by the introduction of high bandwidth memory, which is for some reasons way more energy efficient than DRAM technology. But I think we can only go once from 2D to 3D. Going from 3D to 4D would be something a little more involved, which I can't imagine right now. So we're not sure about the future scaling in this setting over here. I like this view a lot. Now, I always try to break down certain things to its elementary units over here. For quite some time, I had the main question, how to which extent hold these numbers actually true? For 45 nanometers, it was quite difficult because finding processors is not so easy. But just by accident, 7 nanometers is the same technology that NVIDIA used for their A100 GPU. So at some point in time, for a nice Lawrence workshop in the Netherlands last year, I was basically making some math in terms of translating the teraoperations per second and getting some picojoules simply by assuming some data sheet-like numbers. And in a sense, I can simply report that these numbers are definitely plausible because they add up. And there's a short residual regarding the energy if you only compare the computational energy versus the TDP energy, which basically nicely maps to talking to memory. So I would argue that these numbers actually are quite good proxy when it comes to modern processors, at least these GPUs like. So I was kind of reinforced in my point of view of reasoning about picojoules and still being able to have a setting where things add up to the scale that we have at hand when it comes to complete processors or even sets of these processors.
How do you get the number that you list under theory? So what's the theory behind that? How do you know? I mean, just from measurement is not possible to get this number.
The theory comes from this table over here.
Okay. You're assuming that these numbers still are valid for the A100.
I see little reason why the TPU should be fundamentally differently designed to an A100 when it comes to the circuit design of the elementary units. Okay. I would assume that the same science goes in there and the same things hold true. And I mean, there would be some disclaimers for the early TPUs, which I think were not able of floating point operations, but nowadays they also can do. And then the main thing is that I'm tending to see the TPU as a big tensor core unit without the CUDA cores. And some more footnotes, of course, also apply. But possibly a TPU is way simpler than a GPU overall. Might be a disclaimer over here. But actually, I was surprised how nicely these numbers add up. Simply, having this one over here. And if you have different opinions, you can talk to me or yell at me, whatever you would like to do in this particular setting. I was kind of reinforced in my opinion that I have a nice proxy over here with the picojoule per operations.
Picojoule per operation, that pertains really only to the execution of the operation. It does not include the cost for getting the data from the register into the unit, right? That would be counted as memory transfer in your one.
This would be counted as residual. There we actually see that for the CUDA cores, we have a much larger residual than for the tensor cores. The tensor cores are basically matrix operations. The CUDA cores are the vector operations in this setting over here, which in my intuition also makes sense because the vector units always have to talk to the register file, which is a rather large and centralized unit, centralized to a certain set of vector units, while the tensor core units exhibit this array-like pattern where your overall data movement is rather dominated by the PE to PE movement, which should be way cheaper than talking to a register file. If you find a mistake, let me know. I have to admit, I was surprised how nicely these numbers add up. And it was an evening somewhere in Leiden, so possibly I made some mistakes, but I haven't found the mistakes yet. Very well. Basically, I was reinforced in the setting, and then at some point in time, we have a nice research project on, well, green ML was the sales point. And of course, LLMs exist. LLMs are exciting also for us, but our world's a little bit limited because we don't have these 4,000 GPUs for fancy training. So we're rather focusing on, okay, how can we also make LLMs more energy efficient? And in principle, I mean, transition is not so difficult. It just depends on the scale you're measuring. And for the following, I will simply assume that if I have this, if I'm not going to look at this integral, because this integral is basically hard to measure, we're rather assuming that we measure some average power consumption and we integrate over time, or basically multiply by time. And then we basically get a certain energy consumption. And if you want to optimize for energy consumption, the main knob you have as a user when it comes to standard processors is, of course, DVFS. So you vary your frequency and voltage settings and hope that you get somehow a little bit more energy efficient than before. And I actually had some rather involved discussions with actually also many manufacturers, with the main message that they all told me, you can do this, but in our experiments, it never works out. Race to idle is your favorite game to play in this setting. So simply run things at high frequencies. And I was a little bit like, it doesn't make sense. Because if I remember my background education, then in principle, what we're doing in CMOS, what consumes most part of the energy overall, is actually charging capacitors. So we basically always have these transitions from 0 to 1 and back again and all these things. And what I learned at some point in time, that this somehow translates to somehow your switching activity alpha times your effective capacity, so basically the capacitance for all the different units in your chip being summed up, times your voltage squared times frequency. And if I do the math in this context, I basically come up with an answer which basically divides this by the friction frequency. So basically, I'm more or less independent of my frequency. So this is basically the theory. But in practice, I know that things do not work out. So my next question was, where do we deviate from this idealized setting overall? And there are a couple of reasons, actually. So first of all, it would be now the question I would ask my students if there are any gamers in the room who sometimes overclock their processor at home. What did you do while also overclocking your processor in terms of frequency? The typical student answer would be, we also slightly increase the voltage. And I was like, yes, exactly. If you overclock your processor, you have to increase your voltage because you get nicer slopes. And you basically formally have a better approach for time enclosure. And these things actually works in both directions. And so basically frequency depends on the voltage. If the voltage gets involved, we suddenly have a term in our over equation, which is voltage squared, which is definitely going to be painful in terms of energy consumption. Secondly, of course, there's leakage power. So a large fraction of the overall power is simply being lost, even though we don't do anything useful with that. This has gotten down a lot recently. So for the recent GPU experiments, we saw that we have basically an idle power of 20 watts. And I would assume that to a large fraction is actually the leakage power. And this has been way, way worse in the past. So apparently people have been doing some nice jobs over here with clock gating and similar things. And last but not least, we also have other architectural components which are not only processing. So in particular, memory and all these Encore units will, in an easy model, consume some static power, which will also contribute to your overall power consumption. These are basically all reasons which add up somehow to be somehow frequency dependent, while the underlying capacitor charging, decharging should not be frequency dependent. So I was pretty much convinced that we have a dependency on frequency going on over here. And if I create a simple mental model based on these four different terms, then basically my total power is something like my useful switching and my clock and control, my leakage, and basically all the power which goes into the Encore and memory units. And in a simple model I was creating over here just as a sketch without too much science in it, the main message is that as a result we should be observing something like this purple overall curve, which has some kind of a U shape. And this was a point in time where I stumbled with this comment that race to idle is possibly your most important friend when it comes to being more energy efficient. So basically manufacturers tell me, do things as fast as possible. You burn plenty of power, but time will be your friend, so you will consume the lowest energy. This figure here tells me that the reality should be actually looking different. But of course, it depends all on the practical aspects of the processor at hand. And this will be the second part of today, where we're going to explore it a little bit more detail if we see some similar effects when it comes to DVFS tuning for LLM workloads. I know I'm assuming plenty of background knowledge from the audience when it comes to deep neural networks. I simply assume that everyone has a little bit of background knowledge in these things today. Just one quick comment on this workload that we're going to explore in the following. So the transformer is something absolutely fundamental nowadays in deep neural networks, invented as late as 2017. A very nice book called Deep Learning doesn't mention a single time the transformer because the book was published at the same point in time. But basically, in a nutshell, in my personal opinion, the transformer is one of the most powerful methods we have out there in machine learning, simply because the attention module over here is computing a so-called similarity matrix. So this is the matrix product of the Q and the K part. And this similarity matrix comes from information theory and is basically the most powerful tool I can imagine to reason about similarities about two different input vectors, which is exactly what we're doing in these transformer-based architectures. Most powerful one, also in the sense of most power required for that one. So in principle, requirements have been amplified since the introduction of that one, but to a large extent for a good need. And even image processing, the attention module has taken over. So in principle, you can see also the attention module as a generalized form of a convolutional layer. The convolutional layer basically knows that in a certain region, it has to pay attention. In the attention module itself, you basically don't assume the spatial locality effects in terms of the visual interpretation. You basically learn all of them. And with that, basically, you create a mindset or the main assumption that if you have enough training data, an attention module can learn the same thing as someone would handcraft using a convolutional layer, which is actually what happens in practice. So the vision transformer took over in image processing at the cost of more training data. And of course, there's a big set of use cases beyond these forms of visual computing. So vision transformer is no longer used today. This was basically two parts, an encoder and a decoder part. Nowadays, we're basically mostly relying on architectures which are only based on the decoder part, which is shown in the lower part, which is basically, for once, this input, transforming to this embedding, adding some positional encoding, and then this decoder block will repeat a couple of times, which is basically a sequence of this multi-head attention, then some element-wise operations for normalization and similar things. Then your feed-forward part of the model, where you basically blow everything up in the so-called hidden state, which has a certain importance, which actually I haven't understood yet entirely. You repeat this n times, and then basically you have your output model. And this is basically the main message of an LLM, at least in a very simplified settings, which is still reasonably appropriate today. Most recent innovation basically was putting attention on replacing the feed-forward network part with a mixture of experts, which is something more selective, a little bit more sparsity in there. And similarly, plenty of work goes in optimizing the attention module, either in static forms or in dynamic forms. And in my own settings, the flash attention module is possibly one of the most advanced ones in terms of approximating the underlying calculations, which we're not going to do today. We simply stick to this simple decoder structure as we see over here. But if you want to know why you spend these, not billions, more than that, operations and parameters on a certain workload, this here is the underlying structure, which is inherently not so complicated. This here, to a large extent, as said, is the softmax of the similarity matrix. And the feed-forward network is formally an MLP, which basically is two-stage. We blow everything up into a so-called inverse bottleneck by a much, much higher hidden dimension, and then basically translate back again to your typical dimension being formed of the sequence length and your standard hidden dimension of the self-attention module. And this basically exists today in many different flavors. So there's LLaMA from Meta, there's GPT from OpenAI, and many, many more variants, but they're all to a large extent quite similar, and the differences are rather in the detail. So for that part, basically, we connect to the microscale part. In the microscale part, we basically took one of our systems, which is basically a system of 16 GPUs, and 2 GPUs are always interconnected by some NVLink. And the nice thing is basically on premise, like sit in our lab. So we have all the control that we want to have regarding DVFS. So we can basically set any frequency we want. You see over here 15 megahertz steps for the compute part. Unfortunately, for this GPU type, memory is frequency fixed, so we can't play with memory, but we still basically started over here. And in principle, got some early experiments, measured the energy consumption, and got some plots like that one, which simply show you that for many, many repetitions of the same workload, you have some warm-up effects. So beginning power consumption is very, very low. And then basically, these are outliers over here. And then basically, you get to some reasonable standard deviation in terms of your power measurement. Multiplied with the underlying time shall give you some energy consumption. And the main question is that if we play now with DVFS, do we see this U-shape for the transformer, for the decoder block that we were hoping for? And in a nutshell, the answer is, oh yes, we do. We see over here on the highest panel, the runtime with an increasing flock frequency goes exponentially down. Our power consumption goes up until it saturates due to some throttling. And we see kind of a U shape, which for me was immediately suggesting that we possibly don't want to run at the highest frequency. If you reduce frequency a little bit, you definitely can save a certain amount of energy overall. And then you have these different regimes. In the first regime, basically, your clock is too low. So basically, static power contributions will dominate your overall energy consumption. Then you have your sweet spot for the best trade-off. And then you have a setting where basically you have a too high M clock and you will not see proportional return of invest with regards to energy consumption. This is actually holding true for different settings. So we see here a rather small experiment with only 350 million parameters. Oh yes, that is small, I have to mention. So we changed this to one layer from 13 billion parameter model, and we basically saw something which is even a little bit more visible overall in terms of the underlying effects. And then basically, based on that one, we were simply doing many studies on which effects do we see overall, but to a large extent in various settings, we always got the same U-shaped curve. So a different consideration was that changing the sequence length. In the top panel, we see a sequence length of 128. No one is using that today. In the bottom panel, we see a sequence length of 1K, which is also rather small today. And basically observe that we even get a better energy efficiency for the larger sequence lengths, which intuitively makes sense simply because your computations are more involved. So your static contributions will be less overall. Sequence length in general is very important. This here is a graph which is a little bit involved. Sorry for that one. No need to read the small text. This has no message over here. The main message for this plot is actually that we see here basically the different components of one decoder block and corresponding arithmetic intensity, the throughput in operations per second, the total amount of flops, and the runtime, and similar things. And the main message is that you basically have two class operations. One operation class is element-wise, like the normalization and possibly also some simple add operations. And the other one are the similarity metrics or the attention module, the feed-forward pass. And while intuitively everyone thinks that the computational parts like non-element-wise dominate, this is true as long as until you start scaling everything. So at some point in time, element-wise operations will simply become a bottleneck because they simply don't scale with the underlying frequency, which basically means at some point in time, they will form a decent fraction of your overall workload. What does this mean overall for our insights in terms of, well, point one, there is no single best clock. This is one of the major insights that we had up to now. So we actually started to reason about Pareto optimal curves. And for this basically setting, we considered to got our energy over the runtime. So depending on what your key metric is, either you want to do things as fast as possible, or you want to do things with little energy as possible. Basically a two-dimensional objective, a multi-objective, which is very often nicely represented using these Pareto optimal curves. And we basically see over here 4 different experiments. So we vary over here mainly the workload at hand. So within GPT models, we see LLaMA models for Meta, but we always see these V-shaped curves, which basically suggest in combination with the color coding that if your clock is too low, then your runtime will be bad and your energy will be bad. And then as you increase the frequency, you walk down to the pivot point of the V. It will be your minimal energy, not the minimal runtime, but the minimal energy. And from the minimal energy, as you keep increasing your frequency, you will actually increase in frequency, increase in energy, but you will a little bit decrease furthermore in runtime. So if your prime concern is really throughput, so a little energy, as little time as possible, then the highest frequency is definitely the right thing to do. But if you want to minimize for energy, then you have to be a little bit more careful and find the sweet spot. For larger layers, we actually see a softening. So while for small layers on the top over here, there's a rather sharp point, which forms like a V. The larger the model gets, the more we get to the U. If we add on top of this also our sequence length, so if we basically extend the sequence length from 512 to 1K, for some reasons the student also changed the data type to 14.32 over here, we basically see even more softening, that we basically have an even softer transition for low frequencies towards the right. And this is basically for me like super exciting research. Like, yes, we can simply play with DVFS and use DVFS, which is a very easy knob available for us to play with energy optimality, or better said, minimal energy to completion. And in summary, we basically found settings where you can make different trades. But in principle, the common pattern is that you can save something like up to 20% of energy, sometimes 30%, at the cost of a runtime increase. I personally don't care about the runtime increase. So basically, my mindset over here is really only minimal energy to completion. And you can now reason about, does it matter to save 20% or 30%? But people are building nuclear power plants next to data centers. So I would argue that 20% is not a lot. But given the overall power consumption of these systems, it possibly is suddenly a lot. Then my main question was actually, somehow everything depends on finding the right setting. So how can we actually find the right setting? Or in other terms, can we somehow make DVFS settings also a part of our overall workload scheduling? So not only finding the right subset of GPUs somewhere in our cluster, but also tell the system, run these GPUs at a certain DVFS setting. It's a very simple experiment, simply running many experiments to get the data, measure the data. And then we basically trained a very simple random forest predictor on predicting power and runtime, therefore energy, with the main idea we hope that we can use this predictor also in a scheduler setting where basically the system automatically finds out what the right DVFS setting is. And the results over here suggest me that, well, I'm not surprised that these things work out because the machine learning workload nowadays is super static, super predictable. There is basically fixed loop trip iterations, memory access you can perfectly predict, and all these similar things. So from that point of view, I'm not surprised that the machine learning approach to predicting time and power consumption is working out that well. But overall, basically, the next step would be to make it a bit more involved in part of the scheduling, that basically someone decides what is the right setting in terms of DVFS when running these workloads. The main footnote that even though we have these nice results, well, in my opinion, very nice results, we still only have these 16 GPUs. And if you want to train an LLM, 16 GPUs are not of your help. The biggest LLM we trained in our group was having something like 4 billion parameters, which was very nice LLM for Shakespeareization. So if you want to Shakespeareize your text, this can do this very, very well. I think similar things would apply to yoga language, for instance, but it's not completely lacking all these foundational aspects that we are observing in real LLMs. So no, we don't have these resources. And even though I talked to our local head of the computing center, I guess Marcel Evelyn is also a name in Bavaria. Marcel Evelyn?
Yeah, I know him.
Okay, he said, Holger, no, you are not getting 2,000 GPUs for your strange experiments over there. The biggest system we have at university are something like 200 GPUs, and sorry to say, with 200 GPUs in this setting, this is hopeless. At the same point in time, I also argue that it would be definitely wasteful to have this at Heidelberg University because you don't often train these LLMs. So my main idea was everything in LLM is so predictable. Can't we do something else in terms of modeling these things? And this was actually a fun story at some point in time because in a conference, I met a guy from Georgia Tech who wrote a tool called Calculon. And Calculon was basically a tool which simply takes any of these LLM architectures with all their parameters, and we see certain trends in this setting, like in particular sequence length is still trending nowadays, hidden side is no longer so trending, but basically things get larger, have different configurations, and that guy was designing a tool called Calculon, which was predicting everything that happens in the system. Turns out that guy was close to graduation, so he had zero interest in cooperation. And afterwards, he got hired by NVIDIA and had a different task, so he had even less interest or more background noise. But then it turned out that one of my previous PhD students, who was now at NVIDIA, got involved and basically started working on that. And actually, his main idea was exactly in line with my idea. We basically take this decoder architecture, we model every single component analytically. So for every single component, you can basically in a closed form write down how many flag flops, how many memory accesses and similar things. If you have a simple but sufficiently good performance model for the GPU, you possibly, at least for one single iteration of that one, a so-called step or iteration, you could basically model every single component. On top of this, as said, LLM training is easy if you have these 2,000 or 4,000 GPUs. So definitely communication is also a big part of that one. So we also have to model the communication part. Again, the good news, everything is basically predictable. So whenever you need to basically sharpen your attention layer on different GPUs, you know the communication pattern, you know the volume. We have understood collective communication for a long time in HPC settings. So basically we can come up with this corresponding equations for modeling, and basically we can simply model everything up. Well, that's what we did actually in the beginning in combination with NVIDIA. This tool was no longer called Calculon, but GraphCulon. Basically, it's based on modeling everything in terms of systems, the model at hand, and the particular execution configuration. And then you have the scheduler, which implements a certain pipeline, which I'm going to explain in a second. And basically, then analytically, things are being added up, and it simply reports you for so many GPUs and that workload and that configuration, this amount of time you need overall. And the only bad news in this context is that you have to consider many, many different optimization techniques. So there's different forms of parallelism when it comes to LLM training. So people are basically taking the very simplified deep neural network over here. You either replicate it completely. This is something called data level parallelism, which I, as an HPC person, would call embarrassingly parallel. So basically, simply use the same model multiple times for different data. You can use tensor parallelism, where you basically take a single layer and split that one up across multiple GPUs. And of course, you can also interpret the model as a sequence of layers, and different layers go to different GPUs, which is called pipeline parallelism. And in general, people are using combinations of these different forms of parallelism overall, which some people call 3D parallelism, which is a little bit hand-wavy because you basically omit things like expert parallelism or sequence parallelism, or other forms of parallelism. But in a nutshell, it basically gives you already quite a good overview of different options over here. What I think is more involved and also a little bit more interesting are different pipeline schedules, actually. So in deep neural networks, we always have to walk the forward path and then the backward path, and then we compute basically the gradients, and then we do the optimization, then we repeat again and again, which is something we've seen over here in the top panel, that basically you take a mini batch, you split it up in so-called micro batches, and then you basically start over here in the pipeline, you walk down the forward path, at the end of the forward path, you know the current prediction, you find out how good or bad it is by comparing to some whatever ground truth is, and then you walk the backwards path, and then you do the update, iterate things, and this is a code called G-pipe schedule. Yes, you could write papers about that one at some point in time, even so simple. A little bit more involved is the 1F1B pipeline schedule, which has the main idea that we want to minimize the pipeline stores, or better said, formerly the pipeline bubbles over here. The more bubbles you have, the more you're idling. You don't want to idle because this costs you time, or in our setting, it costs you static energy consumption. So there are more involved pipeline schedules, even than that one over here, which simply try to minimize the bubble time while not being wasteful of memory resources. This is basically modeled in GraphCulon. And if you look at the output GraphCulon, these are basically pipelines like that one, which without going too much into detail, nicely reflect our expectations. So we see the forward pass, we see the backward pass, and in the upper part, we actually see some communication patterns, which I was highlighting over here. And once we did this successfully, the only question remaining was the modeling. And in terms of the modeling, basically in a closed form, you can then model your overall iteration time. We see a different experiments for 4,000 GPUs, a mega 1 trillion parameter model, and different traits in terms of fixing the DP, varying the tensor parallelism versus pipeline parallelism. And then you can reason about optimality, and we often see these U-shaped curves. So this is a nice sweet spot when it comes to particular TP versus PP. Very often DP is something which is fixed simply because this only depends on how often you replicate the model. I think the prime question at hand is how good are our results? And from that point of view, we're definitely making still progress on fine-tuning our parameters. So the initial set of models was rather simplistic. So in general, I would argue that this is currently something super helpful for trend exploration. So basically all these trends over here make sense where different components increase and decrease for different overall execution configurations. If you do the one-on-one comparison, I'm just being very candid right now, you will definitely find many, many issues. So we basically had some checks running regarding the fundamental closed form expressions, so how many flops overall, how many parameters. These kind of make sense. We have some analytical models which we explored in detail. So the student did something like 25,000 different configurations, compared them. We interpreted the Calculon results as ground truth results. So can we reproduce them? And we also did some own on-premise experiments. But the main message is currently that there's definitely, let's call it, room for improvement. So I would say the overall trends hold true, but the detailed results definitely show some deviations. I'm mainly blaming some minor implementation issues, that sometimes the interleaving factor, for instance, in the 1F1B schedule is not really fully adhered. And I would also argue that our initial performance model is a little bit too simplistic, which is simply peak performance times efficiency. Efficiency depends on the workload size. It's possibly too simplistic. I'm mainly talking about this today for the main message that is work in progress. So currently in formal collaboration with NVIDIA Research, and there's also a UK-based startup company involved, which has plenty of interest in the communication part. If this is interesting for you, is my main purpose of talking today, then let me know, because there's definitely room for collaboration over here. And I have to say, I have no idea how important LLM workloads are here in Erlangen, but this is possibly something we can discuss afterwards. For me, basically, this is my escape path to make LLM research somehow sustainable in our group without having these GPUs, basically relying rather on these micro experiments plus a macro simulator in combination. And then we have a nice setting where we can study these LLMs like biological objects. If we change something, what happens overall? This is basically my main mindset over here. Because I'm running over time, wrapping up a little bit. So the one thing to notice in this context, just with the general mindset of energy efficiency, this here is a system we set up quite recently. The colors are fancy in the image, in the video. The colors don't mean anything, unfortunately. This is still something being done. I still love this system because basically, as long as your accelerator is PCI Express based, you can instrument every single power connection. So basically, we don't have to rely on vendor tools anymore. Or the main question here is actually to which extent do the vendor tools give us the right experiments, right performance results, power results. Up to now, no big surprise, but this is something which is currently going on in our setting. In general, in our group, we are having different research directions when it comes to deep neural networks. Today, I was most of the time talking about this what we call scalable machine learning, which is basically optimizing for resource efficiency in general, either making things fast or making things small or making things more energy efficient. And this was basically one half of the overall lab. The other half of the lab is more concerned with robust machine learning, which is basically governed by the question, can a deep neural network also give you the answer, I don't know. Picture that you always show some images of cats and dogs and similar things, and then you show something like, I don't know, something never seen before. Formally, the model in this case can't reason about the correct answer. So in my opinion, this can always happen because training data will never be complete. From that point of view, I don't believe in generative AI that much. But then it has to tell you something. This is basically probabilistic modeling or uncertainty-aware deep neural networks. And uncertainty awareness for me is super interesting, but it basically comes at a certain cost. And the cost ranges in between 1 and 5 orders of magnitude. So no, we can't do this with LLMs, but we have some ideas on how to connect that one. My main message for today for you was that I think energy completion is something super promising because point one, there is potential for optimizations over there. Secondly, I would claim that industry doesn't care that much. So even by what they tell you, I think they don't care that much. And I think it's a perfect question for a university. If someone reasons about this one, it should be actually a university. From that point of view, I'm super excited about that one. We have to find better GPUs in terms of more control. But this basically micro experiments in context with LLM training over here, I think has definitely some potential. I'm very much looking forward to possible comments from you on that one. One thing as a head note, not talking about LLM inference yet. Definitely have an opinion that possibly LLM inference is even more important than LLM training. But inference is also much more involved than LLM training. So we have this initial field phase and then the decode phase. And these two phases behave completely different. They behave so different that even NVIDIA is starting to reason about different GPUs, one for the prefill, the other one for the decode phase. So this makes things quite much more complicated, which is something I would rather postpone a little bit for the future. With that one, I hope that this was interesting for you. And many, many thanks for attending. And of course, happy to take some questions.
Right. Thanks a lot. Are there any questions?
Yes, I have plenty of questions, I would say. So I also work on LLM and energy efficiency. So the first thing I've noticed that you choose 1K as the sequence length, right? So I kind of wonder, like, have you tried to scale this to something that's more common these days, like say 8K?
Nope, we are a poor group.
Yeah, but the thing I've observed so far is if you try to scale the sequence list up, things will be quite different, especially in terms of the energy efficiency part. So you no longer get the flops you are expected when you kind of try to scale this up. You need to try all sort of sequence parallelism settings to do that efficiently. And I guess that might be a little bit important to consider, like if we try to make the benchmark more realistic.
So the thing we did was, in terms of our limited possibilities, to scale as much as possible. And anytime we moved from the short sequence length, either 128 or 512, to this, I think, 1K setting, we are actually seeing effects in our favor. So either getting less energy consumption overall, or basically the transition from this V-shaped curve to the U-shaped curve, it basically suggests me that there's possibly even more.
Yeah, I also believe that's probably the case. And I guess I guess I'm also quite interested in trying this out, like see if there's such a U-shaped curve, because I think that makes perfect sense.
Did you say that you are expecting that this basically,
but
the potential will get slower with increasing sequence?
I'm not quite sure, to be honest. I haven't really tried a full-scale experiment for, let's say, 8K, but what you explain really makes sense, and I also really appreciate the point you brought in, like let's say reasoning is this in terms of these very fundamental calculations in hardware.
But we would expect a tension field over here. If we can sequence lengths, then we see direct implications on the self-attention module in terms of overall complexity as well as the FFN part. But I would also argue that these two components benefit more from performance scaling of the GPUs. So even though that possibly today we see basically that the larger fraction of time suddenly goes into this compute-bound part, let's call it like this, while the element operations are rather memory-bound part, I would argue that if we increase future performance of the GPUs, that this will shift back again.
Yeah, I also kind of wonder how the implication of, let's say, stretching on the memory part would bring to the energy efficiency of the LLM. Just wondering, what kind of attention mechanism are you kind of using? Which implementation are you using?
Experiment here?
Yeah, is that
not attention? It's not simulation.
So is that the scaled up product attention as DPA?
Yeah.
Okay.
No paid attention, no fancy approximations based on some rank decomposition or similar things. No optimizations over here.
Would you expect this to change if you switch to flash attention too?
Good question. This is something, if I would comment, I would possibly be wrong on that one. The thing we want to do is definitely change to mix of experts. So this is like the most optimization. But this is something quite simple to model, also in GraphQL. With the flash attention, I would have to start making some statistical measurements and trying to model these statistics somewhere in GraphQL. It's not impossible, but it would be basically something like the next step.
So are you also considering switching to of these sparsity patterns like DeepSeek sparsity attention and other linear implementations like Mamba? I think NVIDIA just published their nanotron model, which is basically a combination of these transformer and Mamba layer. So it's more interesting because it kind of stress less on the memory layer. And I mean, in terms of...
You see, I'm talking to an expert over here. So mix of experts definitely sold on that one. And I'm a big fan of the multi-latent head attention of DeepSeek. It's like my poster child for an approach because it's a learned approach. But many other approaches simply make some assumptions on how your semantic metrics should behave, and then you approximate. But I think it should be a learned approach. And from that point of view, I'm a big fan of the DeepSeek one.
I see.
So this is definitely mentally on the roadmap, but not too involved in practice because it will require some underlying assumptions.
I see. A final question for me
is Mamba.
Yes.
I heard many good things in Mamba about papers. Anytime I saw people using it, they were like,
Yeah, true.
So I'm not sure about state-space models, if they really will be so successful. Either something is still missing, which will possibly come in the future. Probably I'm not too excited about Mamba-like approaches.
I see.
And I mean, if you look at the most recent thing coming from China, this has been the Kimi model, but Kimi is basically DeepSeek, and
Kimi linear has this delta net or Mamba variant added on top. But they're
some variants.
Yes, some variants. Like I think the mechanism itself actually won the best paper of neural IPS this year. So
I'm not up to date on that one. Okay.
So I also find this quite interesting because I mean, since we are now working with a really large let's say key and value memory anymore, like we can expect different energy profiles for it as well. The final question I have is, since you have complete control of the hardware, do you know how much energy would the interconnect cost if you try to move to different types of parallelism? Like, especially for, I guess, for all of these communication phrases, like all of these schemes that could increase all gathers or all-to-all communication, so especially for all-to-all, which is quite important for MOE training. How much increase in terms of energy consumption do you see for interconnect part?
All scales with O of n squared. For all reduced, given the right optimizations, was much better.
Yeah.
And that should be already a disaster. And in terms of communication volume, I'm super interested actually in energy efficient, inefficient interconnection networks, the other one, since 10 years, but no one cared. I'm still on the edge if someone cares today. So on one hand, we also took this ESA lab and measured some InfiniBand cards and tried different settings with the main insight that InfiniBand is energy constant. No matter if you communicate or don't communicate or whatever you do in changing lanes and frequency, it doesn't matter, same energy. So this is energy constant, not energy proportional. In perfect world, it should be, in my opinion, energy proportional. So this is really good news for research. At the same point in time, one InfiniBand card costs you 15 watts. Let's maybe make it 30 for an V-Link network card, something like should exist somewhere, of course, highly integrated. We compare this with 1 kilowatt for a GPU.
I see.
Even if we add the switches on top, like a multi-level switch hierarchy. I think 10 years ago, Google said 20% of the overall energy goes into the network. I would be not surprised if it's less than that today because the processors were getting so energy hungry.
I see.
If you're at High Peak next week, there will be a nice workshop organized by us. We will also talk about interconnection network energy as a side note.
Thank you so much. It's a really interesting talk.
More questions?
I have, but is there anything online?
Not yet, no.
Okay, I have two questions. The first question that you showed is the roadmap, right? The increasing memory consumption, power consumption for memory for HBMs. I find it quite crazy because, as we know, more the power, more the heat generated, and we'll need a lot of cooling. Do you have any idea on the energy consumptions in the photonic chips?
Yes. We love to work with them. Thanks for the question. This could be a more involved answer. So my main interest in photonic computing comes from, it was my major when I was a student, which was a long time ago. But then I gave up on optoelectronics because there was no progress in the community. And since we got a new colleague in Heidelberg, things popped up again because he's building photonic processors. And I remember my back education. And in principle, photonic computing brings you from picojoules, as shown over here, down to potentially dozens of attojoules. So much the theory, or basically some early experiments. From that point of view, super promising because, I mean, from pico to atto, wow, this is actually a lot. This could be a game changer. At the same point in time, everything you do is analog. So basically, you have imperfections, you have noise. In particular, for long sequences of calculations, the noise will add up. And in most settings, or many settings in photonic computing, you can only diminish light. It's very difficult to amplify light. And if your sequence operations is basically always multiplying the weight, which is smaller than 1, light intensity will get less and less and less. The first question is, can we find a neural network where all the parameters have a value of 1 or less? One thing, this is super easy. You just during training clamp the weights to 1. If it's larger than 1, set it to 1. You will find a parameterization in line with that one. For the other part, that your light will get increasingly less intense, this is basically only to be solved by frequent conversion to the electrical domain. And these ADCs and DACs will kill your overall energy efficiency. So I'm super optimistic. Anything existing today, I would basically doubt its use. It's good for early experiments, but it will not give you more energy efficiency today.
All right, that helps.
So the one system we are working with is a chip that size. Super cute. It's operated in a rack. The rack is full of waveform generators, oscilloscopes. 5 PhD students are required to run the system. Not my PhD students, so I'm good.
Did you ever look at this quant hardware?
Baden-Württemberg.
Which is now available in Munich.
In Jülich. Sorry for the Bavarian comment, but also very Jülich. They have a nice website. They have fun CTO, which gives good talks. I didn't learn a single thing about the underlying technology. There are many, many different approaches how you can make computations in the photonic domain. And I have no idea what I think they're formally called QQant, I was told, but I'm not sure about that one. But this is a company which is absolutely obscure to me. So I still like because it's German, Baden-Württembergisch, not Bavaria.
Wir können alles außer Hochdeutsch. Wir können alles außer Hochdeutsch.
This is Baden-Württemberg. So no, I don't know anything about them. Absolutely nothing.
And asked a final question from me. A slide 19. We also use this present form of presentation for a long time, but only the other way around. We plot performance on x-axis, which is 1 over runtime. So we see this bump on the right-hand side. This, what you show here, is a classical indication of a memory-bound code.
Not always.
At the end, it
Frequency is the parameter along the curve. It's not necessarily memory bound.
but then you hit a performance limit and you go up.
Yeah, but you have the same problem because of your cubic or quadratic increase in power as you increase the frequency.
Okay,
Yeah,
but
this optimal frequency in the scale of-
typically this is an indication if
Could also be memory bound, yeah.
so which is not, wouldn't that be big surprise because you use an A30 card, which has quite some FP16 power, but very low bandwidth. Did you do the same measurements on like an A100 or the H100, where you don't have 1 order or 2 orders of magnitudes more FP16 power,
No, because
but much more memory bandwidth?
we did not.
And then that may be a different characteristic.
We did not because setting DVFS is not something which computing centers like, I was told in Heidelberg. So we have the A100 sitting in computing center and they simply say no. And the only thing I can report up now is something more or less breaking from last night with news. This one over here. Basically, I was asking a similar question to the poor student, and basically how much fraction of our workload goes actually where in terms of arithmetic intensity. And for different sequence lengths, again, the small sequence length over here in your standards, I know, but something like 20 to 30% is actually having something surprisingly low arithmetic intensity. But the biggest fraction is still of rather more or less compute bound. I don't remember the details, but I would expect with the tensor cores, compute boundness starts somewhere here.
This is on the A30 or A100?
Everything's A30 here.
Okay.
We have to give people in the Zoom chat a chance. So there's one question. Are you planning to test this on GPUs from other vendors, AMD or even Intel?
With pleasure. Donation request is out. Is the guy from AMD? Can you give us some favor?
NRZ, actually, NRZ. And another question. Since you stated having some experience with FPGA, could FPGA accelerated inference benefit from using custom numeric types for quantized LLMs in terms of throughput, energy efficiency, or resource utilization?
Me, the sweet spot for FPGAs is. Let me start with a quote from the CTO of AMD. FPGAs give you all the flexibility, but you pay for this. It's a nice summary. So FPGAs can do everything. It doesn't mean they can do everything in a fast manner. And so custom quantization could be a sweet spot. At the same point in time, I would argue that we nowadays get from NVIDIA and also AMD. So I'm also a big fan of AMD GPUs. This is something we have to put more attention on. But basically, you already get FP4, and the potential for more improvements is getting less and less. And I mean, there's this one fancy paper out there on 1.76 bit quantization, which is a nice name for something actually ternary quantization. So for int 3 effectively, and 2, I would still see some benefits, but the prospects are getting less and less for the FPGAs. The main issue with FPGAs is that they are notoriously bad on memory. As long as you can keep everything on the chip, FPGAs have their place to be. FPGAs are always very bad to talk to memory, include in particular the external memory, so the DRAM memory. I was complaining, of course, to Xilinx/AMD about that one. And the main answer was that it doesn't have to be like that, but no one cares about it. And I was like, I think many people care. So if you have to choose between the GPUs and FPGAs, I think for most settings of LLMs, GPUs will win over the FPGAs. If you're really interested in some pointers, there's this one paper called Flight LLM, which makes a good case on FPGAs for LLM inference, but with the main message that your batch size has to be super small, like 1. And your key metric is also either power energy consumption. I don't remember the details, but given these constraints, this was some compelling work on FPGAs for LLMs.
There's another question which is connected to that. You initially spoke about quantization and pruning. Can you tell us some experiences with different quantization formats like int4 versus FP8 and NVFP4?
For LLMs, for training, leading result is DeepSeek, which completely trained in floating point 8. It was very surprising to me to see, because there's a big difference between floating point 8 and floating point 16, which is besides that's the current standard. I would argue that you can train in floating point 8, but your overall effort on hyperparameter optimization might be tremendous. So the numbers that DeepSeek reported were absolutely wow. I think they only reported the final training one, but not the training ones leading to the final training one. And I would speculate that plenty of effort goes into the fine-tuning of the hyperparameters. For inference, int4 is a natural constant for LLM inference. int4 does the job for you. There's opq, there's, I forgot the names, but there's a couple of work out there which basically is more or less used in practice for int4 quantization. Everything is post-training, so you don't have to do this during training. Either you have to do a little bit of fine-tuning once. Some other work is being inspired from other work, like looking at the hashing or some hashing approximations to basically find the right quantization without any training. So basically, int4 for inference, FP8 with some footnotes for the training part.
All right. Last question. Sorry, we're massively over time.
You can go, please.
So maybe a quick question. What's your opinion on specialized chips or solutions like from Grok that are tailored towards LLMs?
So Grok is no longer, right?
It's not long.
No, it just was acquired by NVIDIA.
Okay.
Yes.
But do we see already some of their results included, or?
I'm not sure about the training part of LLMs. I think this will be for some time basically the stronghold of GPUs, either AMD or NVIDIA. Besides this training part, I think since 2 years, I'm seeing an increasing growth in options. So there's Grok, there's TensorRent, there's Accelera AI. And they all have a little bit of their own niche, and they all have some similarities. I mean, they're all some kind of linear algebra accelerators. The question for me is mainly how much do they specialize for something particular, and what is the return of investment in this context? So if you would ask me this question 2 years ago, I would be quite frustrated, because what was called the golden age of computer architecture is just their GPUs for the linear algebra and CPU for the other part. And I was like, this doesn't sound like a golden age. Since 2 years, I'm definitely seeing a big increase in, let's even call it diversity. And this is my big hope nowadays, that we now basically see all these startups reaching a point where they're doing something reasonable and contributing their own part. Even though I'm a big fan of GPUs and also NVIDIA GPUs, it was getting too boring for me, the overall setting. So now I'm appreciating that more and more options are adding on the table. The next system we are getting is actually a TensorRent box. We're also going to explore. For me, this is basically something like a GPU with tensor cores without the CUDA cores, a little bit simplified, but even more specialized for the operations. Super curious finding out on how this works out in practice. And very often what these startups also do is they're being way more open-minded regarding software infrastructure. So TensorRent told me everything is open source, everything is adaptable, which is something in the light of something like QDNN is a big plus suddenly. So if you want to do something special, the hope is that now we basically have a much easier approach to doing special things in software than we had before. I'm hopeful. I'm very hopeful.
Thank you. All right. So, well, very last question.
Okay. So it's quite simple and straightforward. Could you go to slide 6, please? Are these widths the same for integer and the floats, like 64-bit? Okay,
I didn't find any numbers.
Okay. Well, my question is regarding FP64 emulation. So does this mean that it's cheaper with using integers? Like if you want to emulate an FP64 operation using integers?
If you want to emulate it, I think emulation would add a certain instruction overhead, which basically spoils your overall efficiency.
Depends on the amount of performance you get from this 8-bit. I mean, there might be no choice in the future when FP64 is.
You want to basically, okay, so you are a scientific computing person, HPC person, which needs floating point 64, even higher precision.
Yeah.
This is a tough setting for you. So the performance scaling of FP64 is stagnating. the future looks bleak. So basically, what a big fraction of at least my colleagues at Heidelberg University from this setting do is they have this interest what they call mixed precision, basically getting to use this low precision as much often as possible, but at very certain but important times, basically relying on higher levels of precision. I'm not a numerical person as involved enough in complex answer, but there should be a plethora of articles these days on what they call mixed precision to overcome this issue over here.
Okay, thank you.